This is my Calculus 1 course. Today we're going to use tables with calculus. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As I mentioned in the previous class, the rest of the course is going to be tying up loose ends, and today's class is an example of that. Today we're going to be covering something that is mostly important for the advanced placement exam. But the concepts are also going to be useful when it comes to the general idea of calculus. So even if you're not going to take the advanced placement exam, this is something that you should probably know. And I left this until the end of the course because it tends to be kind of tedious in some ways. It's not difficult, it's just kind of tedious. So we're going to use our calculators today to assist us. Now I want you to get a picture of the limit laws at the left. We're not really going to use a lot of limit laws today, but I want to reference those and get a picture of the review on the right. So let's review limits. So at the beginning of the course we learned how to find the value of a limit with a graph. So here's an example. So let's say that you have a point on a graph. So you see this point here. We're putting that point on the graph, and this expression here is asking, what do the y values of this point approach as the x values approach 2? So the x values of the point are approaching 2. What are the y values of the point approaching? And the answer is 1. So again, you have that point over here, and the x values of the point are approaching 2. What are the y values approaching? 1. So the value of the limit is 1. So we read the limit of f of x as x approaches 2 from the left is equal to 1. And it's coming from the left because we have that green negative symbol there. So that's how we find the value of a limit using a graph. We also have the situation where we had a continuous function that was defined very clearly inside the limit. And at least it was continuous at this x value, and so we could simply plug in the x value. We're asking, what does this expression approach as x approaches 0? Well, we can just plug in 0 and we have our limit. Again, that's when the function is continuous at that x value that we're approaching. Here's another example. What is this expression approaching as x approaches 2? Well, we can just plug in 2 to the expression and find our limit, which is 3. And we actually make that a limit law. We say that if f is a continuous function at x equals a, then the limit of f of x as x approaches a is equal to f of a. So all that means is that if the function is continuous at x equals a, we can simply plug in a to whatever the expression is to find the limit. That's limit law number 8. But what if the function is not continuous at the x value that we're approaching? Then we have to use what we can refer to as algebraic manipulation. And in that scenario, there's all kinds of different forms of algebraic manipulation. We have factoring, we have expanding an expression, we have multiplying a fraction by an expression whose value is 1, and the purpose of that is to change the form of the fraction so that we can find the value of the limit. And then we have the situation where you're simplifying a complex fraction. We also have other scenarios where we are using trigonometric identities or adding or subtracting fractions in the limit. I didn't have enough room to write examples of those, but the point is there's all kinds of different ways to find the value of a limit. We can also use the limit laws. Here we have the limit of one expression times another expression, and limit law number 3 tells us that that limit is equal to the limit of the first expression times the limit of the second expression. So again, that's limit law number 3, which happens to be this one here. So those are all the different ways that we found the values of limits. But here we have a situation where none of those methods really work. We could graph the expression, and we actually are going to graph it, but graphing is not really practical. It can help us with the concepts, but it takes time to graph a function, and your graph may not be very accurate. So that's not really practical. We are going to graph this expression just so we can understand the concept of what we're doing here. If we try to use algebraic manipulation, well, we just don't have any techniques to deal with this when we have a linear function divided by an exponential function. And if we try to use the limit laws, well, we'd have to use the division law. Then we get the limit of x minus 2 as x approaches 2 over the limit of 4 to the x minus 2 minus 1 as x approaches 2. And if you try to find the values of these limits, well, you're just going to get 0 divided by 0. So the limit laws don't really do anything. But what if we can plug in x equals 2? Let's try that. Then we get 2 minus 2 over 4 to the 2 minus 2. And by the way, this is limit law number 8, right? Scenario number 2 we talked about. So you get 0 over 4 to the 0 minus 1, which is 0 over 1 minus 1, which is 0 divided by 0. So again, none of the methods that we used before are working. So what do? Well, we can use a table. What we can do is we can make x get really close to 2. Really close to 2. And then find the value of this expression. And that's going to be a good estimate of the limit. Again, we can't just plug in 2 because we get 0 divided by 0. The function is not defined there. So we're going to get closer and closer to 2 from the left, and closer and closer to 2 from the right. Now, why do we have to come from both directions? Well, because this is a two-sided limit. In order for a two-sided limit to exist, coming from the left and coming from the right, you should get the same numbers. So we have to come from both directions. Now, if we had just a plus symbol here, then we could just come from the right only. If we had a negative symbol here, we'd come from the left only. But again, this is a two-sided limit. But as you can imagine, finding these values, the values of the expression at these x values, that's going to be kind of tedious, right? So what we're going to do is use our calculators. Now, this is the point in the curriculum, one of the points in the curriculum where a graphing calculator is going to be very useful. If you don't have a graphing calculator, you can still do this, but you're going to have to manually enter in the numbers, and it's going to be kind of tedious. So you can use an iPhone, an Android, or just some old phone from the old calculator from the 1970s. But again, it's going to be kind of tedious. Now, if you have a graphing calculator, it's going to be easier as long as you have a newer calculator. Some of the old graphing calculators, they may not have the same functions that I'm using, so be aware of that. If you're using a Hewlett-Packard or a Casio, you're going to have to figure out how to use those on your own. because I'm going to be using the Texas Instruments TI-84 Plus because that's the most commonly used calculator. So I'm going to show you how to use that calculator if that's the one that you're using. And again, if you're not using this calculator, then a lot of what I'm about to say is going to be kind of a waste of time for you. Your calculator might be similar to this, but you're really going to have to stop the video and figure out how to use your own calculator, and just fast forward through all the stuff that I'm saying. But if you're using a TI-84 Plus, then we're ready to go. So you can press the on button at the bottom left if your calculator is not already on. And then I want you to press the Y equals button, the StatPlot F1 Y equals button at the upper left. And by the way, you might want to press the mode button at the middle upper left and make sure you're in function mode. So go down to the fourth thing on the list, and it should say function and pair and poll. Make sure it says FUNC there and press enter on FUNC. Everything should be highlighted at the left when you push the mode button. Then push the blue second button at the upper left, and then press the mode button again to quit out of that. So now press the Y equals button at the upper left, the F1 StatPlot Y equals button. Now, if there's a function already in there, press clear at the right. And one of the most important tools that you need throughout your math education when it comes to your calculator is the fraction template button. It's very difficult to enter fractions into a calculator if you don't have this template button, because you're going to have to use parentheses, and it can be very difficult, and there's a lot of room for error. So you want to press the green alpha button at the upper left. Now, if you're using a different TI-84 Plus, I don't know if the colors are going to be the same. I'm pretty sure they are the same, but on my calculator, it's the green alpha button at the upper left. Then you're going to press the F1 StatPlot Y equals button, the Y equals button at the upper left again. It's the same button you pushed already. Y equals button at the upper left. Then press enter on number 1. So you should have a fraction template. So now I want you to push the x, t, theta, n button. That's your variable button. And then -2. And then push the down arrow key. So if you're wondering where the arrow keys are, at the right, upper right, you have these arrow keys. I'm sure you can see those. And you can maneuver around using those arrow keys. And so go down and press 4, and then press the upside down V button at the middle right. And that gives you your exponent. So then press the x, t, theta, n button again, and then -2, and then the right arrow key button, and then -1. So see what you can do. Try your best to enter that into your calculator. Every calculator is different, so you're going to come across problems. That's just the way it is. Even with the TI-84 Plus, you may get stuck on a few of these steps, but you just have to spend some time with your calculator. Everybody has to do it. That's why you really need to get used to your calculator now, as opposed to when you're taking an advanced placement test, because that's not going to go well. Okay, so now we're ready to enter our windows. So one of the most annoying things about graphing with these calculators is that if you graph and you have the wrong window, then you have to go back and change the window and graph again. And these calculators really don't graph very quickly in most cases, in a lot of cases. So I have the window for you here. I'm saving you time. So you see this? So press the window button at the upper left. It's the F2 table set window button. Now you see all those buttons below the screen? Y equals, window, zoom, trace, graph. Above the buttons that says stat plot, table set, format, calculate, table, F1, F2, F3, F4, F5. All those buttons right below the screen are for graphing. That's why they're below the screen. So press the window button at F2, upper left, table set F2 window button. Now, you see this here? We have an x minimum of 1, 2, 3, 4, negative 5. So x minimum should be negative 5. So the negative button is at the bottom right. It has parentheses around it and a negative in the middle like that. You see that? That's what it should look like. So negative 5 is your x minimum. And then use the down arrow key. And x max is going to be 1, 2, 3, 4, 5. So positive 5. And then down arrow key. And you can tell what to do here is pretty obvious. Our x minimum is going to be negative 2. Use the negative button at the bottom right. And then the x or the y max will be, we'll say 4. You can say 3 or 4. Those are fine. Now, one common mistake that students make is they accidentally put a negative number for the y max and a positive number for the y min. If you do that, your calculator is going to get confused. Okay, so now we're ready to graph. So we're going to push the graph button at the upper right. The highest button at the upper right. Push that graph button. And you should get something that looks like this. Now your graph doesn't have to be perfect. It doesn't have to be exact. But it should look something like that. Okay, so now that that's in your calculator, we're ready to do some calculations. Now, I want you to push the blue second button at the upper left, the blue second button, and then push the F4 trace button at the upper right, the calculate F4 trace button at the upper right. Then press enter on value, number 1, enter on value, and it says x equals. Now, I want you to enter x equals 2. And the reason I want you to enter 2 is because we're approaching x equals 2, right? So enter 2, and then press enter. And if you'll notice, it says x equals 2 at the bottom of the screen, and it says y equals nothing. There is nothing. Why is that? Well, because when you plug in 2 to this expression, you get 0 divided by 0. The function's not defined there. So we really should have a hole at x equals 2. So I'm going to make that a hole. All right. But what we are going to do is we're going to approach x equals 2. We're not going to let x equal 2. We're going to approach. So press the blue second button at the upper left. Then the trace button again at the upper right. Calculate F4 trace button, and then enter on value. And what we're going to do is we're going to approach x equals 2 from the left. And we're going to approach x equals 2 from the right. So I want you to enter 1.9 and then press enter. And you'll notice that at the bottom right of the screen it says 0.7725. Alright, so let's do it again. Let's press the blue second button at the upper left, then the trace button at the upper right, the calculate F4 trace button, and then press enter. Then enter 1.99 and then press enter at the bottom right. And we have 0.7264. All right. Then push the blue second button again, and then the trace button at the upper right. Press enter. Enter 1.999. Then press enter at the bottom right. And we should get 0.7218. Okay, so x is approaching 2. Now, if I didn't mention, this is a two-sided limit. And that's why we have to approach from the right and the left. If it was a right-sided limit only, if we had a plus sign here or a negative sign, we would only have to approach from one side, but we're approaching from both sides, so we have to show that the limit is the same from both sides. So now we're going to push the blue second button at the upper left, and then the trace button at the upper right, and then enter, and then we're going to enter 2.1, and then enter. And we get 0.6725. Blue second button, trace button, enter 2.01, and just keep doing this. We're going to get closer and closer to x equals 2. And then do that one more time with 2.001, and we get 0.7208. So it looks like the limit of the expression, so you see this green expression up here, that's f of x. The green numbers are approaching somewhere around 0.72 something as x approaches 2 from the left and the right. So in order to get a better approximation, we're going to actually find the average of these numbers. We're going to average those. So 0.7218 plus 0.7208 divided by 2, and let's see what we get when we average those. We get 0.7213. So that is an estimate of the value of the limit. And that's it. That's our answer. So that's how you use a table to estimate the value of a limit. So this hole here, and by the way, that hole should be a little bit lower. Again, it doesn't really matter that much. Your graph doesn't have to be perfect, but looks like it's going to be maybe about there. And again, we need that to be a hole. So the x value of that hole is 2, and the y value of the hole is the value of the limit that we just found. So that is our answer. So as x gets closer and closer to 2, this purple expression here gets closer and closer to a number that is roughly equal to 0.7213. Alright, so as you can see, this is really not that difficult. It's just kind of tedious. Now let's try one more of these. We're going to speed up now because I know we're going kind of slow, but that's because I'm showing you how to use your calculator. Now that you have kind of an idea of how to use your calculator, let's speed up here a little bit. At the upper right, at the upper left, press the y equals F1 stat plot button. And then push the clear button at the upper right. And then press the alpha button, the green alpha button, and then the y equals button at the upper left again. The stat plot F1 y equals button. So green alpha button, and then the stat plot F1 y equals button, and then enter on number 1. And you should have your fraction template. Now notice that we have an e to the x. So how do we write that in our calculator? Well, I think there's a couple different ways, but generally we use the e to the x template button. So press the blue second button at the upper left, and then press the ln button at the bottom left. Bottom left. It looks like this, the ln button, and that should give you e to some power. So again, the blue second button at the upper left, and then at the bottom left, the ln button. Then enter 3 and then x. And again, your x is going to be that button at the upper left, x comma t comma theta comma n button. Then use the right arrow key and then minus and then 2 and then your upside down V button at the middle right. And then your x comma t comma theta comma n button again. And then use your down arrow key and then press the x comma t comma theta comma n button again, and you should have this purple expression here in your calculator at that point. So mess around with your calculator, see what you can do to get that in. And if you have trouble, that's okay. Every student has trouble, because if you're not used to these calculators, it takes time. All right, so if you get stuck, that's completely normal, but that's just something you have to go through to figure out how to use your calculator. Okay, so now we're going to press the window button at the upper left. This is one of the buttons under the screen, the window button. And you see that I have your window right here. So you're going to enter -3, use the negative button at the bottom right, and then 2 for x max, and then for y minimum it's going to be -3, and for y max it's going to be 1, 2, 3, 4, 5, 6, we'll just say 7. So your numbers in your window should be -3, 2, and then -3, 7, and press the graph button at the upper right. At the upper right it says graph, press that, and your graph should look something like this. Again, the graph doesn't have to be perfect. Now, when x approaches 0, you can see again that we have 0 divided by 0 if you do the math on that. So that means that when x equals 0, we should have a hole. So right around there should be a hole. I want to make that bigger than it needs to be just so we can see it. So what we're going to do is we're going to approach from the left. X is going to approach 0 from the left, and x is going to approach 0 from the right. So we're looking for the y value of that hole. We know the x value is 0, right? But what is the y value? So you see the green over here? That's what we're looking for. That y value of that hole is going to be the value of the limit. But again, there is no y value of that graph, so be aware of that. So press the blue second button at the upper left, the blue second button at the upper left, and then the trace button at the upper right. where it says calculate. We're not really going to trace, we're just going to calculate. And then press enter on value. Then press negative 0.1. So remember, the negative button is at the bottom right. Then press enter, and we should get 1.9221. 1.9221. Again, I'm rounding to the nearest 10,000th place. Then press the blue second button at the upper left again, and then the trace button at the upper right, the calculate F4 trace button, and then press enter on value, and then enter negative 0.01. And again, I'm using the negative symbol at the bottom right. That's this symbol here, that button. Or I'm using that negative button there. So then press enter, and we get 2.2647. So if you know how to do this, if you have the idea, go ahead and just enter all your numbers. You don't have to wait for me. So 2.3026. Then press the blue second button at the upper left, and then the upper right, the trace button, and then enter on value, and then enter 0.1, and press enter. And we should get 2.7809, and then do that again, and we get 2.3499. And then press the blue second button at the upper left, and then the trace button at the upper right, and then enter on value, and enter 0.001. And we get 2.3111. Okay, so x is approaching 0. So what we're going to do to find a more accurate number is we're going to have to find the average of those two numbers that we found. So let's see what we get. So add up those numbers, those middle numbers, and double check what you're entering in. Press enter and then divide by 2 and then enter, and we get 2.30685. So I don't really care if you round your final answer to the 10,000th place or not. You can do whatever you want. But that's the number that we get. So that's the value of the limit. That's an estimate. We don't know the exact value, but that's our best estimate based on the table that we have. So that's it. That's how we do this. So you can see that that's kind of tedious having to do all that stuff, especially if you don't know how to use your calculator. If you don't know how to use your calculator, you're probably going to be having some big trouble right now. Calculators are just something that you're going to be expected to know how to use, especially for the advanced placement test. In fact, calculators are required for the advanced placement test. So if you're using something other than a graphing calculator, then that's going to be a problem for the advanced placement test, so just be aware of that. This is the test I'm talking about in the United States. Okay, so now it's time for you to try. Did you learn how to use your TI-84 Plus? Well, we're going to figure that out right now. So go ahead and try number 3. You want to start by pressing the Y equals button at the upper left, and then you want to enter this expression in and see what you can do. So try number 3. When you come back, we'll do it together. Okay, we're back. Okay, so the limit is approximately equal to 1.6094. And we need a hole at x equals 1. So that's going to be somewhere around there. So we came from the left and we came from the right, and the x value of that hole obviously is 1. The y value we don't know, we just estimated it. That's 1.6094. Okay. So if you got that answer, excellent. Okay. So if you got that right, excellent. Now I want you to try number 4. See what you can do with number 4. And when you come back, we'll do it together. Okay, we're back. Okay, if you got that right, excellent. So you can see that's kind of tedious to have to do all that stuff. And that's why I avoided these problems. But we are demonstrating the idea of a limit. And you are learning how to use your calculator, which is very important. So this is very important for you to learn how to do these types of problems. Okay, so we're going to do another type of problem where we use tables. We're going to estimate the instantaneous rate of change of a function at some x value c using selected values in a table. This is a type of problem that you're going to see very often on the advanced placement test. You may only see one of these problems on the test if you take it, but it's pretty common on the advanced placement test. It's not a hard problem, but I just want you to understand the concept. So we have this red function y equals f of x. We have the graph, and the purple line is called a secant line. That line is going through 2 points on the red graph, and the slope of that purple line is called, well, we define it to be the average rate of change of the function f of x from x equals a to x equals b. Okay, that's the average rate of change. Now, if we choose some point with x value c between a and b, and then we find, or let's draw the line that's tangent to the graph at that point. The slope of that orange tangent line is the instantaneous rate of change of the function f of x at x equals c. And what we do is we use the slope of the purple secant line to approximate the slope of the orange tangent line. So we're using the average rate of change between a and b to approximate the instantaneous rate of change of the function at c. Now, as you can see, the slope of the purple line and the slope of the orange line, they're not really the same. The slope of the purple line is going to be positive. The slope of the orange line is going to be negative. So this is not a very good approximation for the instantaneous rate of change. The slope of the purple line is not a good approximation of the slope of the orange line. But what if we move this point here? Now let's draw the tangent line. The slope of the tangent line is, again, the instantaneous rate of change, and now you can see that the slope of the orange line and the slope of the purple line, they look pretty similar. So now the slope of the purple line is a good approximation for the slope of the orange line. So the slope of the secant line, the average rate of change, is a good approximation for the slope of the tangent line, the instantaneous rate of change at C. So this is the principle that we're going to be using in the problems that we're about to do. So it's not something that's hard. Now, because we're going to be using the slope of the secant line to approximate the instantaneous rate of change of the function, we need to look at the formula for the slope of a line. If you have 2 points on the line, in this case these 2 green points, then we use this formula to find the slope of that line. And if you replace x1 comma y1 with a comma f of a and x2 comma y2 with b comma f of b, then you get this expression over here, which we call the difference quotient. Again, it's the average rate of change of the function between x equals a and x equals b. So here's the method that we're going to use, stated here, and you can get a picture of this information if you want, but it's much easier to just do a practice problem, and then you're going to kind of get an idea of what we're doing here. So it says selected values of f of x are given in each table below. Use the tables to approximate f prime of c at x equals c. Okay, so notice that we have limited information. We don't know what f of x is. That's what's different about this problem, is we're only given a table, so we have limited information. Now, if we knew that f of x were equal to something like x squared plus 3, then we could find f prime of x, which is 2x, and then we could find f prime of 4, which is what we're looking for, and that's 8, you see. But the problem is we don't have the expression for the function. All we have is a table. So we have to use the table to approximate f prime of 4. So f prime of 4, the instantaneous rate of change of the function at x equals 4, is going to be approximated using the method that we talked about before. We're going to use the average rate of change. So notice that 4 is between -2 and 5. 4 is between -2 and 5. So we're going to use these two x values and these two corresponding y values. So we're going to say that the instantaneous rate of change of the function at x equals 4 is equal to the difference of the y values of the function divided by the difference of the x values of the function. So that's where I got those numbers. So f of 5 is 15, and f of -2 is 0. And then we have 5 plus 2, and we get 15 over 7. And that's the answer. Now, a lot of students would say, well, can we do this in a different order? Could we subtract like so, and then divide by -2 minus 5? Could we do it that way? And the answer is yes, this works also. So if you look at your slope formula, it's easiest to understand by looking at that formula. So if you have 2 points, x1, y1, and x2, y2, the slope can be written as y2 minus y1 over x2 minus x1, but it can also be written as y1 minus y2 over x1 minus x2. That's fine. But what you cannot do is you cannot say the slope is equal to y2 minus y1 over x1 minus x2. That's not allowed. That won't give you the right number. And you can't say y1 minus y2 over x2 minus x1. That will not give you the right slope. So in other words, you have to subtract in a consistent order. If you subtract the first y value from the second y value, then you have to subtract the first x value from the second x value. If you subtract the second y value from the first y value, you have to subtract the second x value from the first x value. You can't do it this way, where if you subtract the first y value from the second y value, then you can subtract the second y value from the first y value, because that violates the principle of the formula. It is kind of confusing to consider all that, but that's what you have to be careful of. So, but you can do it either this way or this way. They both work. Alright, so let's try another one of these problems. So here we want to find the instantaneous rate of change of the function when x is equal to 37, and that's going to be approximately equal to the average rate of change of the function between or on some interval. Now 37 is between 34 and 40, so we're going to use that interval. So the instantaneous rate of change of the function at x equals 37 is approximately equal to the difference of the y values of those 2 points divided by the difference of the x values. Whoops. So f of 40 is 25, f of 34 is 24, and we have 40 minus 34, so we have 1 over 6. Alright. Okay, so let's try another one. So we're going to approximate the instantaneous rate of change when x is equal to negative 0.3, and notice that negative 0.3 is between negative 0.1 and negative 0.5. So the instantaneous rate of change of the function when x is equal to negative 0.3 is approximately equal to the difference of the y values. Now again, I could start with negative 0.5, or I could start with negative 0.1. It's either way is fine, but whatever you start with, whatever order you're subtracting, you have to follow that same order with your x values, or else you're going to get the wrong number. And then we have negative 0.1, minus negative 0.5. So f of negative 0.1 is 1/4. F of negative 0.5 is 1/2. And then we have negative 0.1 plus 0.5. And we get negative 1/4 over 0.4. And at this point, a lot of students in calculus, they would just use a calculator. That's fine if you want to do that. But we can change 0.4 to 4/10. And then when we simplify that complex fraction, we get negative 5/8. So, as you can see, this is pretty easy. Now again, you could calculate by subtracting in this order. But you would have to reverse the order of the x values also. So if you did it this way, we're not doing it that way, but if you did it that way, then we would get 1/2 minus 1/4 over negative 0.4. That will be 1/4 over negative 4/10. And we would get still negative 5/8. So you can do it that way also. Just be sure that if you're starting with if you're starting with this y value, then you have to use the x value of that corresponding point at the left of the formula. Okay, so now it's time for you to try. As you can see, again, this is really not difficult. We're given a limited amount of information, selected values in a table, and we have to use that information to approximate the instantaneous rate of change of the function at a value that's between two of the x values that are selected in the table. So get a picture of all this information, and I want you to try number 8. So you're looking for the instantaneous rate of change of the function. Whoops, that should be a negative 6. You're looking for the instantaneous rate of change of the function at x equals negative 6. That's going to be approximately equal to the average rate of change of the function between 2 points. So look at negative 6 and try to figure out what x values negative 6 is between. And when you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, go ahead and try number 9. You may have written the order differently. That's fine as long as you ended up with negative 2. If you ended up with positive 2, you may have done something wrong. So try number 9. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. We use these x values and these y values. Okay, go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. Now, a lot of students would just write that in decimal form. You can do that if you want. That would be approximately 4.98 687,664, and it would just go on and on. But you can also turn that into a fraction. So if you're using a TI-84 plus, push the math button at the upper left, and then see where it says number 1 fraction. Press enter on that, and then press enter again, and you get 1900 over 381. And you really could have just multiplied both sides of the fraction by 100 to get that. So if you know you're going to get a huge decimal, you can change to a fraction form, or you can just round off. I don't really care. You write the decimal form and then just round off or something. So we can also say 19 divided by 3.81 is approximately 4.987. Okay, so if you got that right, excellent. So we got these x values from here, and we got the y values from there. Alright, so now we're going to do another problem that uses tables. So we're going to estimate areas with tables. In previous problems in this course, we used Riemann sums to estimate the area between the graph of a function and the x-axis. So we're going to estimate this area, for example, in this particular problem. Again, the area between that red graph and the x-axis. And that area is notated with this notation here. See that notation in blue? By definition, that notation means the area that you see there in green. It's just by definition, that's what that means. Now, in previous classes, we were given the actual function. For example, we would know that f of x was, natural log x or something, or we knew it was 1 over x, or, x cubed minus 2x. And we used the equation for the function to help us approximate the area. But in this problem, we're not given the function. We're just given a table of selected values of the function. So the reason I'm giving you this type of problem is because I want you to get used to this, because these are problems that you'll often see on the advanced placement test, where they only give you a table and then you have to use that table to help you. Another thing that's different about this problem is that when we calculated Riemann sums, the widths of the rectangles were always equal, but you see here that's not the case. The width of this rectangle is 3.5. The width of this rectangle is 1, and the width of this rectangle is 1.5. So the widths of rectangles don't have to be the same when you're calculating Riemann sums. It's still a Riemann sum. And it just means that you're going to get a slightly different number than if you were to use rectangles that have the same widths. Okay, so this is really just the same principle that we used in previous parts of the course. It's nothing different. We're just using, again, the table, and we have different widths. So it says use a left Riemann sum with the 3 subintervals indicated by the data in the table below to approximate that integral. Now notice the fancy word subintervals. On the advanced placement test, they love to use fancy terminology, and they love to use grammar that is very confusing. They're doing that on purpose because they want to trip you up. The word subintervals, let's explain that a little bit. So we have an interval 1 to 7, but then we have subintervals. That will be 3.5 to 7, and 2.5 to 3.5, and 1 to 2.5. So that's what they mean by subintervals. They want 3 subintervals. So as you can see from this picture, we have 3 subintervals. Now, why do they have to use, again, why do they have to use such confusing, fancy terminology? Well, again, they're trying to trip you up. The advanced placement test always does that. I also want you to understand that on the advanced placement test, you're not going to be given a picture. All right? The only reason I'm giving you this picture is to help you understand the concepts. So be aware that this picture is not going to be there when you do this. You're only going to be given the table. So for the first 2 problems that we're going to do, I'm going to give you a picture to illustrate what's happening. But after that, you're going to be expected to be able to do the problem without the picture. All right? So let's do this. Now it says left Riemann sum, right? So that's why the upper left corners of the rectangles are touching the graph of the function f of x. Now again, that red graph is f of x. So if we use a right Riemann sum, then obviously the upper right corners of the rectangles are going to be touching the graph. We're going to do that in the next problem. Compare these 2 problems. You see that the rectangles at the right, the upper right corners are touching the graph, so we'll deal with that later. So let's do this. Again, this problem is not difficult, it's very easy. It's just you need to get used to this type of problem. And even if you're not taking the advanced placement test, this still illustrates some important ideas, so it's still these are still good problems to do. So the integral is approximately equal to the height of the first rectangle times the width of the first rectangle, or you can start with the width, it doesn't matter because of the commutative rule of multiplication, plus the height of the second rectangle times the width of the second rectangle, plus the height of the third rectangle times the width of the third rectangle. Now again, in previous classes, the widths of our rectangles were all the same. That's not the case with these problems. The widths are actually all different. So let's calculate. So we have to know which values to choose in the table because we're using a left Riemann sum. So we're going to use 2 as the height of the first rectangle. So look at the first rectangle and confirm for me that the height of that rectangle is 2. It is 2, right? 1, 2. So we're going to multiply that. That's the height. We're going to multiply that by the width. Now, how do we calculate the width? Well, we can kind of see what the width is. But if you want to do a calculation, you just take 2.5. You take this length, 2.5, and you subtract this red length, 1, and you get 1.5. So this purple 1.5, that's the width of the first rectangle. Does that make sense? 2.5 is the green length. Subtract the red 1, and you get 1.5. So you can just subtract those numbers. So we have 2.5 minus 1. Then we're going to add the height of the second rectangle, which is 5. Now again, you're not going to be given this picture. It's so easy to just go over and look at the picture, right? But again, you're going to need to understand that you're only going to be given the table when we do future problems. So you need to think about the concepts of what we're using in the table also. So that's the height is 5 of the second rectangle. And then we're going to multiply by the width. So the width is just going to be 3.5 minus 2.5. All right, so that is this value here. So then we're going to add the height of the third rectangle, which is 6, and then times the width of the third rectangle, which is 7 minus 3.5. So I'm going to find some more room here. 7 minus 3.5. So let's get some different colors here. We have the height of the third rectangle, and then we're multiplying by the width of the third rectangle. So there you go, that's all this is. As you can see, it's really easy. So we have 2 times 1.5 plus 5 times 1 plus 6 times 3.5. So we have 3 plus 5 plus whatever 6 times 3.5 is, and that's going to be 21. So we end up with 29. That's the estimate for the integral f of x from x equals 1 to x equals 7. The integral of f of x from x equals 1 to x equals 7. So again, we approximated this green area between the x-axis and the graph of f of x from x equals 1 to x equals 7. Okay, so let's do it again. But now we're going to use a right Riemann sum rather than a left Riemann sum. So you see now, because we're using a right Riemann sum, the upper right corners of the rectangles are touching the red graph. You see those pink points there? Or maybe I should make them green. They'll show up better with green. So the upper right corners of the rectangles are hitting the graph. So this is called a right Riemann sum. So let's approximate that area. And you can see that this is going to be an overestimate, because in this part of the graph it looks like the concavity is downward. So the integral of f of x from 1 to 7 is approximately equal to, now what is the height of the first rectangle? The height is actually 5. So we're starting with this number. In the previous problem, we started with this number. You see that? So this is different. So we're starting with 5. And now, what is the width of the first triangle? Well, the width is the same as what it was before. It's just 2.1, 2.5 minus 1. And I should write I should write what we're doing. So h1 times w1 plus h2 times w2 plus h3 times w3. So again, we have the height of the first rectangle is 5, and the width of the first rectangle is 2.5 minus 1. And then we're going to add the height of the, what is the height of the second rectangle? Well, that's 6. And the width is 3.5 minus 2.5, same width that we had before. So you don't have to use colors when you do this. I'm just using the colors to help students see what's going on. It's not necessary to use colors or, to see the colors. Okay, so now what is the height of the next rectangle? The height, you can see the height of the third rectangle is actually 8.3. So 8.3. And how do we know that exactly? Well, obviously I kind of made it easy for you, but you're going to get this information in the table. You're not going to get it from a graph. Again, you're not going to be given the graph when you do these problems. So 8.3 times 7 minus 3.5. So we have the height here and the width. And now all we have to do is calculate. So we have 5 times 1.5 plus 6 times 1 plus 8.3 times 7, actually 3.5, that should be. So now all we have to do is calculate. So 5 times 1.5 is 7.5. Then we have 6. And then 8.3 times 3.5. You can use your calculator for this. That's completely fine to use your calculator. You don't have to do this on paper. So now we just add everything up, and we get 42.55. So you can see that our estimates for the area were quite different. So these approximations are really not that great. The number was way bigger when we had a right Riemann sum. Again, these are just approximations. They may not even be very good approximations, but they're approximations nonetheless. So that's a problem where we had 3 subintervals. Now we're using 2 subintervals to approximate the area between the graph of f of x and the x-axis. And what that means is we're using 2 rectangles to approximate the area. Only 2. So the integral of f of x from x equals 20 to x equals negative 10 is approximately equal to the height of the first rectangle times the width of the first rectangle plus the height of the second rectangle times the width of the second rectangle. So we have the area of the first rectangle plus the area of the second rectangle. So again, we're only using 2 rectangles. And because we're using a left Riemann sum, we're going to start with this number, as opposed to a right Riemann sum where we would start with this number. So we have 10 times the width of the first rectangle. Now, you have to be careful when we're moving from negative 20 to negative 10. You can see that we're moving left to right. X is going from left to right. And so because we're moving from left to right, we need to take negative 12 and subtract negative 20. We have to do it in that order. if we start here at this point and move to here, let's say that that's the width of the rectangle, this being the rectangle, for example, then we're taking the final position and subtracting the initial position. So it's final minus initial. So it has to be -12 minus -20. And that's the way it's going to be with all these problems. We're moving left to right. But if you're moving right to left, you would have to do it the other way. But usually these problems don't really get that difficult, so you don't have to worry about that. Okay, so we have the area of the first rectangle, and then the height of the second rectangle is going to be 1, and the width of the second rectangle is going to be -10 minus -12. Again, we take the number further to the right, or farther to the right, and subtract the number to the left when we calculate the width of each rectangle. Okay, so we have 10 times -12 plus 20 plus 1 times -10 plus 12. That's 10 times 8 plus 1 times 2. And you can move through this more quickly if you want. But we end up with 82. That's our approximation. Okay. So now let's use a right-Riemann sum. Let's do the same thing. We're going to approximate using 2 subintervals, meaning 2 rectangles. And we have the same table, but now we're going to use a right-Riemann sum as opposed to a left-Riemann sum. So all that means is that we're going to start with this number as opposed to starting with this number. So the integral of f of x dx from x equals -20 to x equals -10 is approximately equal to the height of the first rectangle times the width of the first rectangle, and so on and so forth. So we're adding up the areas of 2 rectangles, and the height of the first rectangle again is 1, and the width of the first rectangle is the number farther to the right minus the number to the left. Then we're adding the height of the second rectangle is 5, and we're taking the number farther to the right and subtracting the number farther to the left. So we have 1 times -12 plus 20 plus 5 times -10 plus 12. We have 1 times 8 plus 5 times 2. And we have 8 plus 10, which is 18. So there you go. So you can see that the approximation is really, really different. So again, this is just an approximation, and you're going to get wild numbers if you're only using 2 subintervals. The difference may be huge. So get a picture of these previous problems that we did. Those graphs are going to help you. And get a picture of these problems. And now we're going to try number 15. So notice for number 15, you're not given a graph or a picture of the rectangles that you're going to be using. So this problem will help you with the concepts. But again, you're not given the graph, so you need to understand what you're doing. You're going to use a left Riemann sum, which means you're going to start with this number. You're not going to start with this number. Okay, so go ahead and try number 15, and when you come back we'll do it together. Okay, we're back, and we get 587. So if you got that approximation, excellent. Okay, so I want you to try number 16. Number 16 is the same problem, except now we're using a right Riemann sum instead of a left Riemann sum. So we're going to be starting with this number rather than this number, because it's a right Riemann sum. So starting with this number rather than this number. So try number 16. When you come back, we'll do it together. Okay, we're back. So we get 423. So if you got that answer, excellent. Okay, so that was a problem where we had 4 rectangles, and now I want you to try a problem where we're going to have 5 rectangles. We're using left Riemann sums, so you need to know where to start. And again, 5 subintervals, which means 5 rectangles. Now be sure that the widths of your rectangles are positive. You have some negative numbers here, so you have to be careful. If you do -4 minus -2, well then you're going to get a negative number. In this case, we don't want that. Or that equation is true, but we don't want the negative number. And the reason for that, again, is because we're integrating from left to right. We're starting at -4 and going to 16, and all of these numbers are above the x-axis. The heights are above the x-axis, so we should get positive areas. So, you want to, for the width of the first rectangle, you want to do -2 minus -4, which is +2. That's what you want. So, and then you want that for all the rectangles. So try number 17. When you come back, we'll do it together. Okay, we're back, which is 243. So if you got that right, excellent. Your answer should be 243 on that one. Okay, and you don't have to write the H's and the W's if you don't want to. I probably should have mentioned that. You don't have to do that if you don't want to. So go ahead and try 18. Now we have a right Riemann sum. So we're going to start with this number as opposed to this number. And again, we have 5 rectangles. So try number 18. When you come back, we'll do it together. Okay, we're back. And we have 203. So if you got that right, excellent. Okay, we're going to do one more type of problem. We're going to use calculus and tables to find the values of composite functions. Get a picture of these differentiation formulas if you haven't already done that. We're going to need some of these formulas, especially the chain rule. So it says, use the tables below to find the following values. And the values we're going to be finding are these values here. And we're going to be finding those values given these conditions. So let's do part A. It says, if h of x is equal to f of g of x, find h prime of 3. Notice that this is a composite function. That means we have a function inside another function. And we need to find the derivative of that composite function when x is equal to 3. So when you find the derivative of a composite function, a function within another function, then again we have to use the chain rule. So the chain rule says if h of x is equal to f of g of x, then h prime of x is equal to f prime of g of x times g prime of x. It sounds pretty complicated, but it's just the chain rule that we've been using. So what we're going to do is just rewrite exactly what we just saw. But in order to understand this, let's do the 3 steps of the chain rule. Remember, there's 3 steps. Number 1, find the derivative of the outside function. That's f prime. Number 2, keep the inside function. Don't do anything with the inside function. You're just going to keep it there. Step number 3, multiply by the derivative of the inside function. And there you go. So it's that simple. Now we want to find h prime of 3, so we just let x equal 3. So we just have to find these values. Problem is we don't know how to find those values. We don't have a clue what they are, so we can't do anything. We're stuck. But we have this table over here. That's where the table comes in. So we're going to start with the inside function, g of 3. Let's find that using the table. So this tells us if x is equal to 3, then g of 3 is negative 5. The output of the function is negative 5 if the input is 3. So that is negative 5. So again, just to be clear, g of 3 is negative 5. We can now find g prime of 3. If x is 3, what is g prime? That's 2.5. So if the input is 3, what is the output of g prime? It's 2.5. So we found g prime of 3 is 2.5. Now we need to find f prime of negative 5. If x is negative 5, what is f prime? Well, obviously that is 1/2. So that's 1/2. And 1/2 times 2.5 is 1.25. So there you go. That's how this works. Now you might think to yourself, this is a really weird problem, and it's written in, it's weird because we don't even know what f and g are. So, how is this problem going to be useful in the real world, given that we don't even know what the functions are? Well, this problem, again, a lot of these problems we're doing today are designed specifically for the advanced placement test, and on the advanced placement test you're going to see really weird problems like this. So that's the only reason we're doing this. I left this until the end of the course because, again, I didn't want to give you weird problems like this and confuse you at the beginning of the course. So now let's try this type of thing again. So we have, again, a composite function. We have a function inside another function. The outside function is the purple g, the inside function is the green x squared. So this is different from the previous problem because we know what the inside function is. It's defined, x squared. In the previous problem, we didn't know what the function was. We just had a name for the function. It was called g. Again, g is the inside function on part A. X squared is the inside function in part B. Also, another thing that's different about this problem is in the previous problem, the outside function was called f, and the outside function in this problem is g. So it just depends on how it's written. But let's use the chain rule because we want to find k prime of 6. So we need to find the derivative of that function. So k prime of x, we need to use our 3 steps. So step number 1 of the chain rule is to find the derivative of the outside function. That's g prime. Step number 2 is to keep the inside function. Don't do anything to it. And step number 3 is to multiply by the derivative of the inside function. So the derivative of the inside function is 2x. All that stuff there became 2x. And just to reduce any confusion, probably be best to write 2x first. Although you don't really have to do that. Okay, so now we're ready to go. Let's find k prime of 6. Why are we finding k prime of 6? Well, because that's what the problem is asking for. So we just need to replace x with 6. And forgot to write. So we have 2 times 6. And then, so again, I'm plugging in 6 for x. And then we get 12 times g prime of 36. So now we have to find g prime of 36. So when x is 36, what is the output for g prime? Well, that's 9. So we have 12 times 9, which is 108. So there you go. It's that simple. Again, I know this is a weird problem, but you're going to have weird problems on the advanced placement test. We're not going to cover all the types of problems that you're going to see on the advanced placement test, because that would be a whole nother course. Maybe not a whole nother course, but it would be a lot of time. So let's see. So now we have, again, a function within a function. In the previous problem, the inside function was defined. Actually, up here, the inside function was defined. It was x squared. Here, the inside function is not defined. It's just named f. In the previous problem, the outside function was not defined. It was just called g. But in this problem, the outside function is defined. It's actually the root function. So these problems take a lot of different forms. So before we do anything, I'm going to change that expression to f of x to the 1/2 power, because that just makes it easier for us to find the derivative. So remember, when we use the chain rule, we find the derivative of the outside function. So we're going to use the power rule to do that. So we found the derivative of the outside function. That's step number 1. Step number 2 is to keep the inside function. Notice f of x doesn't change. Step number 3 is to multiply by the derivative of the inside function, and of course that's f prime of x. Okay, so now all we have to do is find f prime of 36. We're going to replace x with 36, because again, that's what we're looking for. Okay, so we need to find f of 36. If x is 36, what is f? Well, that's 2. And then we need to find f prime of 36. So if x is 36, what is f prime? That's 1. Okay, so we don't have a lot of room, but this is going to be 1/2 times 1/2 to the 1/2. And 2 to the 1/2 power is root 2. And if we multiply both sides of this by root 2, we're going to end up with root 2 over 4. If you don't know how we got to root 2 over 4, you can go to my beginning algebra course where we talk about how to rationalize denominators. I think I also talk about that in my intermediate algebra course. So there you go. That's how those problems are done. So we're going to do another problem like that. And then you'll have a couple of these to do on your own, and then we'll be done for the day, and you can start your homework. So, same type of problem. We need to find h prime of -6, but we can't do that until we find the h prime function. So we're going to find the derivative of the outside function, keep the inside function, and then multiply by the derivative of the inside function. Again, it's 3 steps for the chain rule. You always use the chain rule when you have a composite function. So now we're going to replace x with -6. And then we're going to use the table to help us find these values. So f of -6 is 10. So f of -6 was 10. F prime of -6 is -1. And maybe we should use brackets there. You don't have to, but it helps to see. G prime of 10. If x is 10, then what is g prime? That's 2. So we have 2 times -1, and we get -2. So there you go. I know these problems seem kind of confusing, but that's the way they're supposed to appear, because this is the advanced placement. These are in the style of the advanced placement test. Okay, let's try this next problem. In this next problem, the inside function is actually defined. We know what it is. It's 3x plus 5. Whereas in the previous problem, the inside function was not defined. It was named. It's named f, but we don't know what it actually was. In this problem, the outside function is not defined. We don't know what it is. We just have a name for it. We have f. Whereas in this problem, the outside function was g, again, not defined. We just had a name for it. So, but because we have a function inside another function, when we find the derivative, we have to use the chain rule. So, the first step of the chain rule is to find the derivative of the outside. So that's just f prime. The second step of the chain rule is to keep the inside function. Don't do anything with it, just keep it there. And third step of the chain rule is to find the derivative of the inside function and then multiply that by everything that we just found. So the derivative of 3x plus 5 is 3. So all of this became that. So I'm going to rewrite that by putting the 3 in front. That will just reduce confusion. And now we replace x with -1. So we have 3 times f prime of 3 times -1 plus 5. And if we do the math, we get 2. 3 times -1 is -3. -3 plus 5 is 2. So we can probably show that work. I don't really think it's necessary, but so we have 3 times f prime of -3 plus 5, which is 3 times f prime of 2. Now we just have to figure out what f prime of 2 is. So when x is 2, what is f prime? That's 12. So we have 3 times 12, which is 36. So there's another problem where we had to find the derivative of a composite function. A composite function is just an expression where you have one function inside another function. So we got 36. Okay, now let's do part C. So in this problem, the outside function is actually defined. We know what it is. It's e. Whereas in the previous problem, the outside function was not defined. We just had a name. We called it f, but we didn't know actually what it was. In this problem, we don't know what the inside function is. We just call it g, but we don't know what it is. But in the previous problem, the inside function was defined. Now, again, in the first problem, neither the inside function nor the outside function was defined. So, a lot of different variations of these problems. So, we're going to use the chain rule because we have a function inside another function. G of x is the inside function, e is the outside function. So, step number 1 of the chain rule is to find the derivative of the outside function. The derivative of e to the x is just e to the x. Remember, it's the only function that doesn't really change if you find the derivative. So that's step number 1, is find the derivative of the outside function. Step number 2 is to keep the inside function. And step number 3 is to multiply by the derivative of the inside function. So now we just have to find b prime of 2. So we just replace x with 2. And now we go to our table. If x is 2, then what is g? Well, that's 0. So we have e to the 0 power times, if x is 2, what is g prime? Well, that's 4. So all of that becomes 4. Anything raised to the 0 power is 1. And there we go, we have our answer. So I want you to get a picture of these problems, and you're going to try a problem set like this. So get a picture of these, and get a picture of the differentiation formulas. Okay, so try number 21. And when you come back, we'll do it together. Okay, we're back. Okay, so if you got those right, excellent. Go ahead and try number 22, and when you come back, we'll do it together. Okay, we're back. Okay, if you got those answers, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and 4 and 5, 6, 7, 8, 9, 10, and 11. But don't go before you get your homework. So here's the homework. Get a screenshot of this page here. That's screenshot number 1 and screenshot number 2 and screenshot number 3 and number 4 and number 5 and number 6. Now I'm going to zoom in on these tables in case you have trouble seeing those numbers. So that's 14 and this is 15. Alright, and we have one more problem here. So get a screenshot of number 16. And again, I'm going to zoom in on that table. But don't go before you get the answers. It's not enough just to attempt the homework. It must be done correctly, so you have to check all your answers. Here's the answers. So do that homework completely, correctly, neatly, and keep it in order in your binder, and I'll look forward to seeing you in the next class.